Hi everyone. In this video we are going to start looking at how we can encode logic in Agda, for example, or any other dependency type programming language. So in a traditional programming language you usually have your program, and if you're lucky you have a specification what the program is supposed to do. But there is a very clear divide between these two things. So the program is something you give to your computer, so it's represented formally and precisely in your computer, whereas the specification is usually represented just on paper and is for you to read and for others to read, but there's no formal checks and there's no guarantees that the specification actually makes any kind of sense. Whereas if you have a syntax error over here, then the compiler will catch it, right? So this is how things are in mainstream languages today. But the picture in a dependently typed programming language is quite different. So here we can take the specification, and instead of having it separately on a piece of paper, we can actually move it into the program so that the program and the specification are both represented formally in your computer. But in order to do this, we of course need a way to represent specifications which we can identify with logical formulae for the purposes of this video in the language. So just like we can represent programs in our language, it is a programming language after all, we also need a way to represent specifications, that is logic, in the language. Okay, so how do we do this? So in languages you might have seen before, if someone says logic, you might instinctively think, oh, logic, that's this Boolean thing, right? True and false, etc. So this is probably our first thought, that we say, okay, let's use Booleans to represent logic, which means, because there's only two Booleans, true and false, that means that we're saying that a logical formula is either true or false, right? Okay, so let's see if we can do this. This is how we would represent a set of Booleans in Agda. So it's data declaration. You can also find this in data.bool, but here I copied it in so we can see what it looks like, and we have two constructors, false and true, right? Okay, and then if you want to, so that's fine for atomic logical formulas, false and true, but most specifications are not just going to say, well, this is always false or this is always true. We want to combine different statements, right? And we can get quite far by defining these combinations of logical formula using pattern matching. So here, for example, I've defined AND using pattern matching. So I'm saying that if the first one is false, then the whole thing is going to be false. So this equation takes care of that. And if the first one is true, then the truth value of the whole thing is going to be the same as the truth value of the second thing. So if the second one is true, then the whole thing is true, and if the second one is false, then the whole thing is false. So that's capturing AND of Boolean formulas quite accurately, right? And we can do the same for OR and for implication and for all these kinds of things. So that's fine. But what about if we want to say that the specification should talk about all inputs, for example? So for all natural numbers or for all strings or something like this. So we want to specify not just what happens for a finite number of things, but what happens for here an infinite number of things for every natural number, right? And then we see that we have a problem because we have to take all of these specifications P of n, and then we have to give back either true or false for if it holds for every n. But of course we have no way of checking this infinitely many specification formulas in finite time, and we have to do it in finite time because we have finite people. And that's a general problem with saying that propositions are the same as Booleans, because that builds into the logic that we represent decidable properties. Because if I have a program of type bool, then I can always run it and it's going to return false or true for me, right? So I can always decide if it's true or not just by running the program if I represent logic as bool. But sometimes in order to have interesting specifications, we might even want to have these specifications to not be decidable. And then we're going to spend some effort and prove that they are satisfied. But that's effort we're willing to spend. We don't necessarily want the computer to do it automatically for us. So that's the problem with saying that propositions are the same as Booleans. So let's look at another way to do this, which is the standard way to do this in type theory. This is called propositions as types. And our starting point is a more philosophical question. What is a proposition exactly? So here we said that the proposition is true or false, and we saw that that leads to saying that possibly this is not really a proposition, because how can we say if this is true or false? I mean, you might philosophically believe that it's either true or false, but you don't know which one it is. But for practical purposes, we actually want to represent it, right? And then if we say that it's either true or false, then in order to make this proposition, you have to tell me if it's true or false or not. So that's one philosophical standpoint. It doesn't work so well if you want to actually convince a computer that something is a proposition, but I mean, fine if you want. But here's another way to say that a proposition is anything that you possibly could hope to prove. Right? It doesn't have to be true, but you'll at least know what the proof of it would look like. Right? So it's a little bit like the famous saying about pornography, that pornography is something you know when you see it. And in the case of propositions, a proposition is something you know when you see what the proof of it could be. Right? But if you go with that idea, then we make the intellectual leap and we say that if a proposition is something which might have a proof, then we might as well identify the proposition with the collection of proofs that it has. So instead of talking about the proposition directly, we can just talk about the proofs of it, because we said that this is basically the same thing anyway. So that then says that to be a proposition is nothing else than being a set of proofs. So we can make this identification. We say that, well, propositions are just sets or types. The set is here the Agda name for types, right? And if we make that identification, then we're also led to say that a proof is nothing else but a program of the right type. Right? Okay, so let's see if we can go with this idea. I mean, it sounds a bit crazy, but maybe it works. So the very least we should be able to do is to represent the standard logical connectives using this idea. Right? So implication, conjunction, etc. So let's start with implication in this video. So the question is, what is a proof of A implies B? And if you think about it, well, it should be a method for turning proofs of A into proofs of B. Right? So in order for me to convince you that A implies B, that means that if you tell me that A is true, then and give me some evidence for it, then I should be able to tell you that B is true and give you some evidence for it. And it could be that you can't tell me that A is true, and then it's easy for me to do it. But in general, I should be able to take the proof of A that you give me and turn it into proof of B so that I can give back to you. Right? So it's a method for converting proofs of A into proofs of B. But that, of course, sounds a lot like a function from A to B. Right? So we can just say that we implement implication as function. Okay, so let's see if this works. So as a very first example, we would expect that A implies A, right? So let's see if we can prove this. Okay, so we are asked to prove the goal A implies A. Well, it's a function, that's what we said. So I'm going to introduce an argument on the left. I reload the file, and now I have to give an A. I look at my context and I see that I have an A, so I can just return that A. So see that the logical fact that A implies A is implemented here by the identity function. Right? So that's why I named this I. So it's worked so far. We can represent the fact that A implies A at least. Let's see if we can do a more complicated example. So here I have A, B, C, D, and I have some formula implying some other formula. Okay, so what do I have? I have two arguments. I'm going to call this F and G. Then I reload the file. And now I say I have to produce a D. I look at my context. Okay, I see that F will give me a D if I give it something. So I'll do F question mark, give that. Okay, so now here I have to give the thing that F expects. And I see that it's a function. So it's going to be lambda a, b goes to something. Reload. Okay, and now I have to produce a C. And I see what I have. Well, G will give me a C if I give it something. Okay, and now I have to give an A, but I do have an A. Okay, so I could finish this. So what I did was I wrote a program, but that program corresponds to a proof. So I've proven this logical statement by writing a program. So that's making use of this fact that they're identifying programs and proofs in this setting.